course of real-time embedded system. Today we are going to start chapter number 6, lecture number 17, and in this chapter we are going to discuss about interfacing. As stated in previous chapter, we use processor to implement processing, memory to implement storage, and buses to implement communication. The earlier chapter described processor and memory. This chapter describes implementing communication with buses known as interfacing. Communication is transfer of data among processors and memories. For example, a general purpose processor reading or writing a memory is a common form of communication. A general purpose processor reading or writing a peripheral is another form of communication. In this chapter, we began defining some basic communication concepts. We then introduced several issues relating to common tasks of interfacing to a general purpose processor, addressing interrupts and direct memory access. We also described several schemes of arbitration among multiple processors, attempting to access a single bus or memory simultaneously. We show many systems may include several hierarchical organized buses. We then discuss some more advanced communication principles and survey several common serial, parallel, and wireless communication protocols. As I've told you in the beginning of this chapter that we use embedded system for the purpose of processing, storage, and communication. In processing, we do transformation of data with the help of processors. In storage, we retain data and we use memory for that purpose. In communication, transfer of data between processors and memories, and we implement this with the help of buses, which we call interfaces. Okay, so that is the thing which we are going to discuss in this chapter, interfacing. In this slide, we will talk about a simple bus. So let's first talk about wires. What are wires and what are buses? So wires can be unidirectional or bidirectional. As you can see in this figure, the first three lines are unidirectional, pointing towards one side, whereas the last one is bidirectional, pointing towards both processor and memories. One line may represent multiple wires. So you can see here some lines are thick and some lines are thin. So the thick one represent multiple lines, okay, and the thin ones is a single line. Bus. So bus is a set of wires with a single function. For example, address bus. So on address bus we will have addresses. On data bus we will have data. So here you can see we have 0 to 7. It means like we have 8 bits of data, so 8 different lines. Here we have 12 bit of address, so 12 different lines, but these are all combined together because their function is single. So set of wire with single function is known as bus, or entire collection of wires. So all these lines can also be called bus. So we can combine all these: add, address, data, and control. These are two control signals. This one is your enable, this one is read write. So these two are control signal and rest of these two are address and data. So every bus has associated protocols, means the rule for communication that must follow. So every bus has some associated rules. So in this slide we are going to discuss about ports. As you can see here in this figure, the port is pointed out with this arrow. The bus connect ports of processor or memory. The port is actual conducting device like metal on the periphery of a processor through which signal is input or output from the processor. A port may refer to single wire or a set of wires with single function, as I've told you. For example, 12 wire address port, 7 wire data port. So this is 12 wire address port and this is 8 wire data port. So the related term for port is pin. When a processor is packed as its own IC, there are actual pins extending from package, and those pins are often designed to be plugged into a socket on the printed circuit board. As you might have seen sometimes the processor, so the one side of processor has lots of pins that are extending out of it. So what we do, we put it in a socket on the printed circuit board. So these pins are also called ports. Today, metal pads connecting processor and memory within single IC. So nowadays we use metal pads for connecting processor and memories on a single IC. So that was about the ports. Let's move on to next slide. So in this slide we will talk about the timing diagrams, and we will talk about two protocols, that is read protocol and write protocol, and you can see the timing diagrams of both these protocols on your right hand side. The most common method for describing a hardware protocol is timing diagram. So we use timing diagram to describe the hardware protocol or the communication protocol. In this diagram, you can see time proceed to right on x-axis. So time is proceeding to right side on the x-axis. So in both these diagrams, control signals are either high or low. So these are control signal, read write, enable. So these control signal are either high or low. Okay. Maybe active low. So active low is defined by go dash slash go or go underscore low. So these are all active low, and this is how we usually define signal from low to high, this shape. So we use the term assert for active and deassert for low. So when we have to say like the device is asserting, it means it is high or active, and once we say it is deassert, it means that it is low or zero. So asserting go dash means go is equal to 0. So when we have go complement, it means that go is equal to 0, it means it is low. Okay. So data signal not valid or valid. So data signal can either be valid or not valid, and this is how we represent the data signal. Protocol may have sub-protocol. So a single protocol, for example, this is a communication protocol. So single communication protocol can have sub-protocol, and these sub-protocols are read and write. And we also call bus cycle, for example, read and write. Each may be several clock cycles. So each read and write protocol can be several clock cycles. Here in read example, as you can see here, I'm going to just explain the read example, and the write protocol is exactly the same as our read protocol. So for read bar, as you can see here, read bar, so this signal is going to be 0 throughout the reading process. So rd dash slash wr set low, address plus on the adder for at least t setup time before enable asserted. So here you can see that our enable is asserted here. So we are going to place the address on the address line at least t setup time before the enable. So here from this point, I'm just going to mark, here we have the enable signal asserted, and here we have t setup time. So this is the difference. So we have to put the address on the adder before the enable. So how much time we need to put the address on the address tab line? It's t setup time. Now, enable triggers memory to place data on data wires. So when enable is high, it triggers memory to place data on data wire. So this is the time. So in this time, this is the time. In this time, we must need to place data on the data wire. So there are two times that we need to put. When enable signal is high, we need to have at least t setup time before we have put the data on the header bus, and once enable signal is high, we need to put data on the data bus after t read time. Okay, so there are two times here. One is t read, another is t setup. So similarly for the write protocol, so here you can see that we have for write we need to have write signal 1, and similarly we have enable. So enable is going high here. So before that, what we need to do, we need to put address on the address bus. So this is t setup time before the enable, and because this is the write protocol, so what we are going to do, we're going to put data on the data wire. At the same time, we are going to read the address. So however, the writing will start here. So writing will start here once we have the enable signal. So once we have the enable signal, this is t write. So we must need to write during this phase. Okay, we can write during this phase. So that was about timing diagrams of reading and writing protocols. So let's move on to next slide. So in this slide, we're going to talk about the basic protocol concepts. The processor memory protocol described earlier was simple. It has read protocol and write protocol. Hardware protocol can be much more complex. However, we can understand these better by defining some basic protocol concepts. These concepts are actor, direction, addresses, and multiplexing. So actor is a processor or memory involved in the data transfer. A protocol typically involves two actors, master and slave. A master initiates the data transfer. A servant, usually called slave, responds to initiation request. So our GPU, that is our processor, is master, and our memory or peripherals are slaves as shown in this diagram. Master is your processor, servant is your slave. It can be your memory, it can be peripheral. Data direction. Data direction basically denotes the direction that the transfer data moves between. So it moves between sender and receiver as shown in the figure. Addresses represent special kind of data used to indicate where the regular data should go to or come from. So from where the data should go or come from. So specifies a memory location, a peripheral, or register within the peripheral. So these are the addresses where the data can go in a location in memory, a peripheral or register, or within peripheral. In time multiplexing, we share a single set of wires for multiple pieces of data. So here you can see that we are using single piece of wire for multiple pieces of data. We are sending header, address, and as well as we are sending data. Slave wires at the expense of time. So we can save wires. So we do not need a separate wire for address or for data. So what we can do, we can save wire. So in this example, you can see that we are serializing the data. So it means that we have just 8 bit of data transfer bus. What we are doing, we have 16 bit of data. So we are serializing data. First we are sending the upper 8 bits, and then we are sending the lower 8 bits at the second clock cycle. Whereas here, if you see in the second diagram, first the processor send request to the servant, and then we multiplex. Here we were multiplexing the data, the upper bits and the lower bits. Here we are multiplexing the address and data, and at the receiver we were demultiplexing it. So at the receiver we are demultiplexing it. So request clock cycle, at first clock cycle we are sending address, in second clock cycle we are sending the data. So this is address data multiplexing, whereas this is data serializing. So that was about basic protocol concept on a hardware level. Let's move on to next slide. So in this slide we are going to talk about the control methods of protocols. So we are going to talk about basic protocol concepts. Control method. Control methods are schemes for initializing and ending the transfer. Two of the most common methods are strobe and handshake. As you can see here, one method is strobe and one method is handshake. So these both are control methods. When we have to initiate and we have to end the data, we can use any of these protocols, either strobe or handshake. Strobe protocol, the master uses one control line, often called request. So here you can see that master using one control line, often called request. Use this line to initiate data transfer, and transfer is considered to be complete after some fixed time interval. So after some fixed time interval, the transfer is going to be complete. So request is sent, and once receiver receives this request, it is sending the data to the master. So here are few steps, and after these steps I'm going to explain you this time diagram. Master asserts request to receive data. Assert means signal high. REQ to receive data. So the request is asserted. Servant puts data on bus within time axis. So during this time, request is sent. So this is 1. Now, what does the servant do? Servant puts data on the data bus during this time. So this is t axis time from here to 2. Master receives the data and deassert request. So here the data is received, so it will deassert. So this is number 3. Servant ready for next request. So servant is now free and it is ready for next request. So at 4 the servant will be free. So at 1 master assert request. At 2 data is put on the address bus. How much time is required is t axis time. At 3 the master deassert after receiving the data, and at number 4 servant is ready for next request. The second common control method is handshake. As the name says that handshake, in handshake we usually use acknowledgement signal. So the second most common control method is handshake protocol, in which master uses request, so master is using request to initiate the transfer, and servant uses acknowledgement line to inform master when data is ready. So here at 1, I'm just going to go through these first, the points, and then we will look at the timing diagram. So master assert request to receive data. So similar thing. Servant puts data on bus and asserts acknowledgement signal. So this is almost same thing. However, here we do not have to wait for some specific time. Previously we have to wait for t axis time before the data was put on the data bus. Here we'll put data on the data bus after acknowledgement. So here 1, in 2 the servant is asserting the acknowledgement signal. Okay, so this is the acknowledgement signal, and once it asserts the acknowledgement signal, we are sending the data or putting data on the bus at the same time kind of. In 3 master received data, so data is received, so master will deassert request. So here the request of DZ is sent. Now here at 4 the servant will be ready for next request, and here we have the end of data receiving. So you can see the difference between control method. In one we have to wait for like t access time, in other the servant send the acknowledgement signal and asserts and send data on the data bus. So that is the difference between store protocol and the handshake protocol. Let's move on to next slide. So in this slide we are going to talk about the compromise between the store control and handshake protocol. So here you can see that we have master, we have servant, the same request signal, the same data signal, and here we have wait. So this is the T access wait. So in fast response we are not going to for the wait signal, like we are not going to consider the wait signal, whereas in slow response we are going to consider the wait signal. So here in this, and let me go through these points first. Master assert request to receive data. So master request to receive the data by signaling REQ. Servant puts data on data bus within T access time. So after this time the servant will put data on the data bus. And wait line is unused, as you can see that we are not using the wait line. Master received data and desert request. So now the signal of request is going down. At this, after some time at 4 the servant will be ready to request some other master. Now whereas in this diagram there is the slow response case. Now master assert request to receive data. So master request servant to receive data by asserting the REQ signal. Servant can't put data within T access time. So servant is unable to put data in T access time because we have a wait signal enabled. Assert wait acknowledgement. So here the wait signal is acknowledged. So wait acknowledgement. At 3 servant puts data on bus and deassert wait. So at 3 here you can see when the here we are putting the data on the data bus at 3 and deasserting the wait signal. At 4 master receive data and deassert. So at 4 master will deassert the request signal, and at 5 the servant will be ready for next request. So here we have like, here we do not have to wait, we just have to wait for T access time and servant puts the data on the bus within T access time. Here servant cannot put the data on during the T access time, rather it will wait for acknowledgement signal. Okay, so this is slow one, this is fast one, and that's the compromise between store and handshake because we are using both the things here. Okay, let's move on to next slide. So in this slide we are going to talk about ISA bus protocol memory access. So ISA stands for Industry Standard Architecture. It is an architecture for memory access. It is common in 8086 base system. You can see here that we have microprocessor, memory and IO devices all connected to ISA standard bus. It features 20-bit address and it uses the strobe handshake control protocol. So it's a compromise strobe / handshake protocol. 4 cycle by default. It has 4 cycle, as you can see here, C1, C2, C3 and C4 is after C3. Unless channel ready deasserted, resulting in additional wait cycle up to 6 cycle. So as long as this channel ready signal is not deasserted, we will have 4 cycle, otherwise we will have 6 cycle. So this is cycle, these are clock signal up and down, and then this is data 0 to 8, this is address 0 to 19, and this is address latch enable signal, and this is our / memory. It means that is going to work at low, and then this is our channel ready. So this is memory read bus cycle using ISA bus protocol, and this is our memory write bus protocol using ISA bus protocol. So in clock 1, microprocessor puts a 20-bit memory address on address line. So during clock 1, microprocessor puts 20-bit address on the address line and asserts this signal As you can see here, this signal is asserted and the address is put on the address bus. In the second clock cycle, here you can see, during the second clock cycle and third clock cycle, C2 and C3, the memory read signal, so C2 and C3 till here, the memory read signal send request to read operation from memory device. So we are going to read from C2, C3. During this time, we are going to read from the memory. After C3, the memory device holds the data on data line. So after C3, you can see here, the data line holds the data. At C4, all the signals are deasserted. So I do not have space here, so that's why otherwise the C4 will be after here. So let me recap this thing one more time. So just forget about channel ready, because unless channel ready deasserted, so channel ready, if you see here, the channel ready is high here, the channel ready is high here. Okay, so only during the C2 cycle it is low. So unless channel ready deasserted, resulting in additional wait cycles up to 6. So if it is deasserted, we will have 6 cycle, otherwise we will have normally 4 cycle and a wait. So this is telling you that after this deassert we have to wait. Okay, so initially we are putting the data on the address on the address line, and then we are latching the address because we are going to put this address all the time, C1, C2, C3, all the time on the address line. So we have to latch this, and then we have the memory read signal to request a read operation. So we have to read the data, so we have the memory read signal. So after like C2, it is going to read the data till here, C3, and after C3 we are putting the data on the data bus. You can see here data, and after C4 all the signals are deasserted. Here in memory write bus cycle, you can see we are putting the data address on the address line, we are enabling the latch, and then what is happening actually, after latching we are memory write, so we are telling which memory to write. So once this memory write signal is low, we are writing during cycle 2, cycle 3, and that's it. And we are using a wait because of this channel ready. So like whenever we have a channel ready low, we will have to wait. So if there are like 2 channel ready low signals, then we have to wait for longer time. So once the data is written, all the signals are deasserted. So that is typically what is happening in ISA. We have cycle, we have clock, we have data, we have address, we have memory read write, and then we have channel ready. These are the standard configuration of ISA. So let's move on to next slide. So in this slide we are going to talk about microprocessor interfacing, that is I/O addressing, input-output addressing. A microprocessor may have tens or hundreds of pins, many of which are control pins, such as pin for clock input and other pin for resetting the microprocessor. Many of the other pins are used to communicate data to and from microprocessor, which we call processor IOs. Okay, there are two methods for using pins to support IOs. Number one method is port based, which we also call parallel input output. Processor has one or more n bits ports. So processor can have multiple n bits ports. Processor's software reads and writes a port just like register. For example, these are the example for reading and writing on the register. P0 is equal to 0 cross FF. It means 255. So we are putting this value on the port P0, and this is like V is equal to P1 dot 2. So we are defining the port 1 pin 2 is equal to in V. So P0 and P1 are 8-bit ports. So we read and write on a port just like a register. Whereas in bus-based I/O, processor has address, data and control ports. So we have all kinds of ports that form a single bus. So a single bus consists of address, data and control ports, as I have told you in the beginning of this lecture. Communication protocol is built into the processor hardware. So we physically build the communication protocol onto the processor. A single instruction carries out the read or write protocol on the bus. Let's move on to next slide. So here few compromises and extensions are shown for parallel I/O, that is our port based I/O, and then we have the second one, that is bus based I/O. So in parallel I/O peripheral, as you can see here, we have processor is connected to memory through system bus, and then this system bus is connected to parallel I/O peripherals with port A, port B, port C. So we call this parallel I/O peripheral. When processor only support bus based, so processor is only supporting this bus based I/O. But what is required? We require parallel I/O. So we are going to use this module, parallel I/O peripheral. Each port on peripherals connected to a register within the peripheral. So this port is connected to a register in the peripheral that is written to or read by the processor. Whereas in extended parallel I/O, you can see here that we have processor and we have in fact 1, 2, 3 and 4 ports. What we want to extend the number of ports. So what we can do, we can use parallel I/O interface with any of the ports. For example, in this port 3 we are using parallel I/O peripheral. So we have additional port A, port B, port C. So extending 4 ports to 6 ports. Now here the processor is supporting the bus based. So when processor support port based, but more ports are needed. So it is supporting port based, but we are needing more ports. In previous case it was supporting bus based, we were needing ports. So this is the compromises and extension of input output addressings. Let's move on to next slide. So in this slide the 8051 interfacing is shown. Here you can see we have 8051 microprocessor, that is port 0, that is address latch enable, and then we have port 2, this is write signal, control signal, this is read signal, and this is some other control input, control port, and then this is linked to, this is our data memory 0 to 7 you can see, and the addresses are 0 to 15, and this is our program memory and the addresses are from 0 to 14, and this is 0 to 7. So we are not going to, here the timing diagram is shown for the data memory. So what we are doing here, so the addresses and data are multiplex. So port 1 and port 2 support port based input output when 8051 internal memory being used. So here we are using, because interfacing an 8051 to external memory. So we are not using internal memory. In fact, the external memory is being interfaced. So port 0 and port 2 support port based. So here in this case they are not supporting port based because we are using external memory. These ports serve as data address buses when external memory is being used. So these serve as buses. So here you can see in port 0 we have address from 0 to 7, and then we have data, that is our 8-bit data. So 8-bit address, 8-bit data, and in P2, in port 2, you can see here in port 2 we have an address from 8 to 15. So what we are going to do, we are going to latch this address. So this address will be on the address bus. So for that we are using this address latch enable. So when address latch enable is enabled, we are going to hold this address, that is from 0 to 7, and then we are going to combine this address with this address, and finally our read signal will assert and we are going to read the data. Okay, so 16-bit address and 8-bit data are multiplexed. So 16-bit address and 8-bit data are multiplexed. Low 8-bit of addresses must therefore be latched. So therefore we are latching the lower 8 bits. These are being latched with the aid of ALE. So in this diagram we are just showing you that for internal memory we are going to use that it is programmed like P0 and P2 are used as a port based, but because we have like external memory, so we are going to use P0 and P2 as bus based. And this is the timing diagram of how the addresses and data are being placed or picked. So that was about the interfacing. Thank you very much.